Welcome back to my YouTube channel. In the course of this video lesson, I'll be teaching on a very important aspect in chemistry, and this aspect is simply called chemical equilibrium. And in the course of this video lesson, I'll be solving different practice questions that cut across this topic from the scratch. So let's get straight into this video lesson. So the first question we ask ourselves under this particular topic is what chemical equilibrium is all about. But before we talk about what chemical equilibrium actually is, it is important for us to break the topic, which is chemical equilibrium, into two important words I can see in the topic. And the words are, the first one is chemical, so we take note of it. So we have to know what chemical is all about. And the other word here is equilibrium. All right, so it is important for us to understand perfectly what these terms are all about before we can join them together to define what chemical equilibrium is all about. So listen carefully. So moving over to the first term here, which is chemical. Now listen carefully. The word chemical can be either, listen, the word chemical can actually be an element because elements are chemicals, and also the word chemical can also be a compound. So please listen carefully. The word chemical can be an element, and the word chemical can also be a compound. So now listen carefully. From introductory chemistry, an element and also a compound falls under an umbrella word called a substance. So we can simply say here that the word chemical simply means substance, because chemical can be an element or a compound. An element and compound falls under this umbrella terminology called a substance. I believe you are following me. Now, moving over to the term equilibrium. Equilibrium simply means balance. So please just take note of this. Equilibrium here simply means what? Balance. A state of balance. Are you there? So you can see we've successfully broken down the two words chemical and equilibrium. So from what we've gotten, we can just join them together to define what chemical equilibrium is all about. But after joining and defining, I'll give you the appropriate definition to take note of. So moving further, bringing these words together, we can simply say here that chemical equilibrium is a state where there is a balance between substances. These substances can be either an element or a compound. Now, this state where there is a balance between a substance, whereby the substance can be either an element or a compound, all occurs in a reaction. So defining what chemical equilibrium is can now be: chemical equilibrium is a state where there is a balance between substances in a reaction. Are you there? So that's what it is from just bringing the words together. But it is time for us to understand perfectly what chemical equilibrium is, so we can start analyzing every aspect of this topic. So this must be noted about chemical equilibrium. Now listen very well. Chemical equilibrium, listen, chemical equilibrium is a state in a chemical reaction. Is a state in a what? Chemical reaction, and I'm going to show you what I mean by a chemical reaction. You just listen carefully. All right, we just said that chemical equilibrium is a state in a chemical reaction where the rate, listen, you can say I brought out another word, is a state in a chemical reaction where the rate, all right, for rate, I'm going to write it in a capital letter. So I explain to you what this actually means, or rate actually implies in chemical equilibrium, all right, is a state in a chemical reaction where the rate, listen, of the forward reaction. The word forward reaction, I'm still going to explain to you what it is. Where the rate of the forward reaction, listen very well, where the rate of the forward reaction equals, listen, equals the backward reaction, equals the backward reaction. And I'm going to explain what I mean by all this. So you just listen carefully. So look at what I said. This is the definition for chemical equilibrium. Chemical equilibrium is a state. Is a state in here, in a reaction, in a chemical reaction. It's not a state when two persons are playing football. It's not a, I'm talking about chemical equilibrium now. It is not also a state where there is a tug of war, where we have people on two sides trying to drag and try to defeat each other. That's not what chemical equilibrium is all about. Chemical equilibrium is a state in a reaction, in a chemical reaction, where the rate, which I will emphasize on, of the forward reaction equals the backward reaction. Now listen very well. From this place, which is the rate of the forward reaction equals the backward reaction, from here, forward reaction equals the backward reaction, I can simply just rephrase it and say where the rates of the forward and backward reaction are balanced. Because remember we said that equilibrium has to do with balance. You get, so I can say rate of forward reaction and backward reaction are equal. I am correct. I can also say where the rate of the forward and as well as the backward reaction are balanced. I am also correct. But there are some terminologies here you should take note of. The first one is rate, the other is forward reaction, and the other is backward reaction. You have to understand what all these are talking about. So listen very well. Now, it is very important for me to explain to you what is happening in a chemical reaction that is in equilibrium. So you just listen very well. Now let's take an example. Let's say for instance, now for this first example, I will not be using elements, I'll just be using symbols to represent elements. So you just watch. Let's say A now is reacting with B. Now, there's also something you should take note of whenever we talk about chemical equilibrium. The reactions that are explained under this topic, chemical equilibrium, are simply called reversible reaction. Wow. This is another terminology you should take note of. Now, this is what I said. The reactions that are explained here, the chemical reactions we are talking about here, they are specifically called reversible reaction, and I'll be explaining to you what a reversible reaction is. So you just listen very well. I'll be explaining to you what we call a reversible reaction. So the question we ask ourselves, what is a reversible reaction? Very simple. A reversible reaction, from the word reversible, listen, a reversible reaction is a reaction that can proceed in the forward and backward direction. You just listen very well. So I just explained to you that whenever we are on the topic chemical equilibrium, that chemical reaction we are talking about is not like your regular reactions you used to know, but I'm going to explain everything. The reactions we are interested here is what we call reversible reaction, and a reversible reaction is a reaction that can proceed in the forward and backward direction. The reaction can go forward and also return back. So let me explain. Now, before I write this reaction on the board, I have to tell you something. In a reversible reaction, we see a sign. Actually, when we see that, we know that, oh, that reaction is a reversible reaction. And what do we see to know if a reaction is reversible? And I'll be telling you now. That sign is simply called, listen very well, that sign is simply called reversibility sign. What did I say? That sign is simply called reversibility sign. How do we know a reversibility sign? Here is the sign. So you just listen very well. I'll be drawing it in a box. In a reaction wherever you see two arrows, one coming forward and the other going backward, you simply say that reaction is reversible. Just listen very well. Take note of that thing I just wrote there, and I'll be explaining to you what it actually means. So moving further, you can see here that I said that chemical equilibrium is a state in a chemical reaction. What type of reaction are we interested in? Reversible reactions. How do we know reversible reaction? We'll see a sign, and that sign is called reversibility sign, and here is the sign. Now listen. So A and B are reacting together. Definitely they will form a product. Relax, I will explain. Remember, normally in a regular chemical reaction, we will just see a sign that looks like this. You see one arrow just going forward. This arrow, this is not what we see in the topic chemical equilibrium, because I told you that in chemical equilibrium, we are working with reversible reactions. We don't see this. You understand? We don't actually use this sign. This sign is simply called your yield sign. You understand, in chemistry, but that is called reversibility sign. And what did I tell us we are interested in on this topic? Reversible reactions, and we deal with reversibility sign. So what should be here should be reversibility sign. Just relax and I will explain. So you can see here that I have removed that yield sign that you used to know, because in chemical equilibrium we deal with that sign, reversibility sign, because our reaction is reversible in chemical equilibrium. So here is the sign we are interested in. This sign, I'm going to write it very big so you see what I'm talking about. And this is another one. You can see the first one is going forward, and this other one is coming backward. You can see how it is. You can see the first one going forward and the other one coming backward. So let's say A and B reacted, and with the reversibility sign, A and B reacted, they gave rise to, listen, they gave rise to C plus D. You can see here now, I'm not talking about like a regular reaction, all right? I'm not using, elements. I'm just using symbols so you understand what I'm talking about. So now this reaction you are seeing now, what do we call this reaction? We call it a reversible reaction. Now this must be noted. You must understand here that reversible reactions are of two parts. In a reversible reaction, we have two parts in a reversible reaction. We have the forward part and as well as the backward part. So this reversible reaction you are seeing here, they are two parts. All right, it gives rise to two different reactions. The first one is called the forward reaction. All right, the first one is called the forward reaction, whereby the other one is called the backward reaction. So you just listen, and they are all very easy. So let me explain to you what I mean by all this. So you can see A and B, they are reacting to give rise to C and D. So you can see the first arrow is going in the forward direction, whereby the other arrow is going backward. So this first arrow is simply called the forward reaction. All right, this first arrow is simply called the forward reaction. Take note of it. whereby the arrow that is coming backward, we simply call it the backward reaction, because you have to note something now. So in this reaction you are seeing now, a question can come and they will say, provide the forward reaction for this reversible reaction, and as well as provide the backward reaction for this same reaction. Let's solve the question. So let's say solution. Listen. So they said we should provide both forward and backward reaction for this reaction. So let's provide the forward first, and I will explain to you how it works. So here is the forward reaction based on what I'm saying. Forward is coming from AB to give me CD. Backward is coming from CD to give me AB. It's coming backward. So for forward AB, listen. So A plus B. Listen very well, to give me C plus D. And then you are not surprised. Why did I now write one arrow? Because I've broken the reaction. So I'm allowed to write one arrow here. This is just a yield sign. Because the question says we should break it. We should provide the forward part of it and as well as the backward. So in providing the forward, always make sure you put one arrow. You understand? Don't have to put two arrows. So if you do that reaction, you are rewriting what they gave you. I believe you understand. So now for backward, the reaction is coming backward. So the backward reaction will now be this coming backward. So it's coming backward. We'll start like this as well. C plus D, because it's coming backward. So C plus D will give me A plus B. I believe you are following. It's very easy. So you can see we provided both the forward and backward reaction for this reversible reaction. So the next example I'll be bringing is a proper chemical reaction. So now listen very well, and I have to tell you something. I have to tell you something that is very key. All right. You can see I said that a chemical equilibrium is a state in a chemical reaction where the rate of the forward, you can see I've not emphasized on the word rate, or the forward I've emphasized on forward, and the backward reaction are equal or are balanced. So what does rate mean? Rate talks about how fast something occurs. So bringing rate into a chemical reaction, it talks about how fast, let's say for instance, this reaction can occur. How fast? So talking deeply into this reaction, rate implies how fast can A and B. Now, I believe you know here that in a chemical reaction, we have two sides. We have the reactant side. In a chemical reaction, this is your reactant side, and this is your product side. So now, rate has to do with how fast this reaction can occur. Now, talking about rate deeply now, it talks about how fast our reactant can form our product, and also how fast our products can form back our reactant. That's what rate talks about. I believe you understand now. And also I believe you understand how this was explained. I'll be bringing more proper reactions to explain. I'll solve another, I'll give you your own to practice. So get ready for your own practice question. In the course of this lesson, I'm going to bring a lot of practice questions so you solve, so master this topic properly. Okay guys, moving further, here is another example to understand perfectly the forward and backward reaction in a reversible reaction on the topic chemical equilibrium. I'll be solving one, I'll give you one practice question, so we'll go over to another concept in the course of this lesson. So watch closely. Here is a reaction whereby NO2, listen very well, this is NO2. Now in the course of this lesson, I'm not telling you what it means, the name of the compound. I'll just basically write it. NO2 is a compound, and for you to know a reaction that is reversible, you must see this sign, reversibility sign, one going forward and the other one coming backward, and it's giving me what we call N2O4. Now, you must also ensure that whenever you're solving questions on all of these aspects, you should ensure that the reaction is balanced. Now, looking at this reaction is not balanced. I already have a full video lesson here on my channel that explains how to balance chemical reactions like this and more other practice examples. So after watching this lesson, because I'll just balance this quickly, go watch my full video lesson on how to balance reaction. Here's the video lesson on my channel. So let's go straight into this particular reaction to balance it and then provide the forward and backward. I believe you already know that this arrow up is your forward and also the forward reaction. Now there is something you will just use to denote reaction. You can see what I just wrote. Reaction, listen very well. Reaction can be symbolized as arrow and this symbol like alpha and n. You can see what I just wrote. You can see I just wrote forward reaction. So you just know that okay, reaction is this, is same as this. So when I write it, you understand what I mean. So this is the forward and this is the backward. This is the forward and this is the backward reaction. You understand? So let's balance first of all. Now you have to observe both sides of the reaction. I explain all the steps to be taken when balancing chemical reaction in this lesson. So make sure you go watch that lesson. But in balancing reactions, you must check the atoms of the elements at both sides of the reaction. In a reaction, we have two sides, the reactant side and the product side, or we can call it the left-hand side and the right-hand side. So just listen. In the left-hand side, how many nitrogen can I see? One nitrogen. In the right-hand side, how many nitrogen can I see? Two nitrogen. So I have to make sure I balance that nitrogen that is not balanced, because here is one, here is two. So what do I do? And I explained that in that lesson that whenever you're balancing reactions, you don't write numbers inside the element. You only write numbers at the front. You understand? So if here is 2 and here is 1, what should I do to this to balance it? Definitely I will put 2 in the front. Because if I put 2, it will balance nitrogen. Nitrogen now becomes 2 because 2 now is affecting everything, not just nitrogen, is affecting oxygen. This is unbalancing reaction. I've explained it in that video. So go watch it to understand perfectly how to balance reactions. So basically, looking at this, 2 nitrogen and nitrogen is balanced because initially it was 2 oxygen. So me putting 2 in the front, this 2 is times anything in C's. So 2 has times this oxygen that was 2. So 2 times 2, that's 4. 4. You can see oxygen is 4, so oxygen is balanced. Nitrogen is 2. Nitrogen is 2. Nitrogen is balanced. So in all, the reaction is balanced. So let's go straight into writing the forward and backward reaction. So first of all, let's just do for the forward reaction. I believe you know forward is going from this to that. Forward. You understand? So basically it's 2NO2 to give me, I told you it's one arrow, right? N2O4. But for the backward reaction, it's going backward from this to this. So N2O4 to now give me, it's coming backward, all right, 2NO2. You understand? So this is the forward and backward reaction for this reaction. I'll be giving you one practice example and you provide the answer in the comment section, so we'll go over to another concept in this topic. Okay guys, here is another practice example, all right. It deals with sulfur 4 oxide, SO2, all right, reacting with oxygen gas, O2, on the reversibility sign, all right, it's giving me SO3, but the reaction is not balanced, all right, because here we're having 4 oxygen, 2 plus 2, 4, and 3 oxygen. Here it's not balanced. Just relax. I'm going to help you. Here is 2, because when I put, 2 is affecting everything, so 2 has affected sulfur, so it's best I put 2 here as well, because we're now having 2 sulfur, 2 sulfur. I told you always add numbers in the front. You don't add numbers inside. Don't do that. Only at the front. Go and watch that lesson to understand perfectly how balancing reactions works. All right. So in turn, we are having how many oxygen here? 2 times 2, 4. 4 plus this 2 oxygen, 6 oxygen. 2 times 3, 6 oxygen. Oxygen is balanced, so everything here is balanced. So you provide the forward and backward reaction for this reaction at equilibrium. So move over to more concepts on this topic, all right? And the concept we'll be talking about next is how to write equilibrium constant expression for reactions. You just relax and I'm going to explain how it works. All right, let's go straight into that concept. Okay, guys, let's move straight into this concept. It is very important for us to understand this concept under this topic, and it is simply called writing equilibrium constant expressions for reactions. So first of all, it is important for us to understand the concept of equilibrium constant expression, and this is very key for you to take note of. Now you should know here that equilibrium constant expression has a symbol to which it is noted. Listen, equilibrium constant expression is symbolized as K, all right, EQ. Listen very well. Equilibrium constant expression is symbolized as what? KEQ. Just listen. All right. Now, this KEQ you are seeing now is divided into two. I will come to that very soon. But it is very important for us to understand first how to write equilibrium constant expression on general basis. So take note of this. So equilibrium constant expression is symbolized as what? KEQ. Okay guys, moving further, since we've noted that equilibrium constant expression is symbolized as KEQ, now is important for us to understand how to actually write out the equilibrium constant expression for reactions. So you just listen now. KEQ, which is equilibrium constant expression, has a formula that must be noted. In writing the equilibrium constant expression for reactions, it has a formula. What is the formula? Is what I'm about writing on the board. And the formula is equal to product. You just listen. Products. All right. And I believe I've told you the product side of a reaction. The right hand side is the product, whereby the left hand side is your reactant side. So KQ is simply equal to product divided by reactant. Please take note of this, is going to help you greatly. We have to start from the scratch. So let's take an example. You just watch. Let's say, for instance, this element A, though it's not a proper element, just a symbol. I'm using symbols first before I go over to real reactions. So element A is reacting with element B. All right, and then listen very well. With the reversibility sign, which shows that the reaction is at equilibrium, it gave rise to C plus D. And let's say, for instance, it has coefficients. You know, in the normal chemical reactions, there are numbers, you know, to show the balancing of the reaction. So let's say we have coefficients. Those coefficients, they call them numbers. You just listen. So let's say the coefficient here is letter n, like the number. Normally we used to have numbers now. You saw those reactions were balancing. So let's call them the number or the symbol or the alphabet or coefficient. The right word is coefficient. A number standing in front of, you know, a reaction is a coefficient. You understand? So same applies. This has also its own coefficient, which is n in this case. Let's say this one's coefficient is p, and this one's coefficient is Q. So let's assume this is a chemical reaction, because this question can come at your exam the way it is. They'll say, write the equilibrium constant expression for this reaction, and it is very simple. And what's the formula for equilibrium constant expression? Again, I just told you, it is product divided by reactant. And I believe I've shown you that in a reaction, the right hand side is the product, whereby the left hand side is the reactant. So you just listen. So the first part of our formula is product. Let's focus on our product. In this case, we have two products. In some other case, we may have just one product. In some other case, we may have 3, 4 products. As the case may be, you have to write for what you have. So this is how it works. The first product I am seeing is C, with its coefficients to be P. Listen very well. Now, this is how it works. My product is what I'm having up. So I will just do the formula to divide it into two based on how we have it. So we already have the line that divides it. This is product, this is reactor. So let's focus on the product. You write individually for the product. The first product is C. I'm going to write C. Are you there? Now the next thing. That C you have written, put it inside a bracket. There is a reason. As we progress further, I will explain to you the reason. Put it inside a bracket, and this is how you write the brackets. Follow instructions. Moving further, the next step to take, your coefficient, the letter, the number that is standing in front of what you've picked, should be raised as the power. So basically, what's the coefficient P? I've raised it to be the power. This is how it works. Actually, explanation is from what we call the law of mass action. But just note it. So you can see I've written for one product. I said write for the individual products. For instance, this was the only product I am done with product. I'll focus on my reactor, but I have another product. So to go over to the next product, you times. And the way we show the times is using dots. These dots here symbolize times. But we don't just write times, we use dots, you understand. Note what I just said. So you can see we are done one product. Let's go back to the next product, same step. So write the element which is D, all right, open a bracket. The coefficient should be raised as the power. What's the coefficient? Q. I've raised it to be the power. I am done with the product side. Let's go over to the reactant side. These are my reactant. And the first reactant I'm having is A. And what's the coefficient? Open the bracket, put it inside. What's the coefficient? M. I've raised it to be the power with your times. All right, go over to B. Write B, put it inside the bracket, and raise it to the power of the coefficient, which is N. And this is the answer to this question. This is what we call the equilibrium constant expression for this reaction. The way I solve this is how you solve any other reaction. But I'm going to help you and teach you some rudiments, some things you should note. So this is the first example. I'm going to give you your own practice example right away. So you solve, we'll go over to more practice example. So here is your own practice example. This place I'm having A, I'll remove it. This place I'm having B. I'll just remove everything and just rewrite any other symbols. Let me see how well you understood what we said. I believe you understand. So here, I'll be using Z plus, let's say Q to give me P plus, let's say, arrow. And now these are the coefficients. All right, let's just say here is ox. Let's say here is y. Let's say here is t, and let's say here is s. So you can, these are another reaction. So you provide the equilibrium constant expression based on what I've explained. Let's go over to more practice example. Okay, guys, let's get into another practice example. And here is the example now. It is the element Hi. All right, is being dissociated, is being broken down to form H2 gas plus iodine gas. So you can see I'm taking note of their states of matter. This will help us. All right, this is also a gas, but it's not balanced. So it's best I put 2 in the front, because if I do that, we now have 2 hydrogen balanced, 2 iodine, and 2 iodine balanced. Go watch my lesson on how to balance reactions to understand perfectly how all this works. Now, it's very important. What I'm about saying now is very key. I beg you, take note of it, all right? You can see now we have started writing the equilibrium constant expression for reactions, regular normal reactions that have, elements. So now there's something you should note, all right? Let's take note of it. In writing the equilibrium constant expression for reaction KEQ, I'm going to divide it into 2 parts. Listen very well. Whenever you are writing equilibrium constant expression for a reaction, this must be noted. You should ensure here that gas and aqueous species, gas species, they symbolize them as G. Aqueous species, they symbolize them as AQ. You see them in all of these examples of a bringing. Gas and aqueous species appears, just take note of it, appears whenever we are writing the equilibrium constant expression. Note it and I will apply it. They appear in the expression. You understand? They appear whenever we are writing that expression. But there's something that do not appear. And what is that? Listen. Now, everyone take note of this. Solids and liquid species. So anything solid, anything liquid do not appear whenever you are writing the equilibrium constant expressions for reactions. All right, they do not appear. Now, this is what we take them to be. The reason why they don't appear is can be an exam question. The reason why solid and liquid species in a reaction do not appear because they are taken to be one. They are regarded as one. Listen, solid and liquid species do not appear in a reaction. Why? Because they are regarded as one. So based on what I've explained, let's solve this question. First of all, in solving questions that pertain to this aspect, check their state. You can see all of them are all G, meaning they are all gases. And what did I tell you about gases? They appear in the expression. And the reaction is balanced. And also, this must be noted. In a reaction, let's say you do not see any number or any coefficient, because you can see here that the coefficient for HI is 2 based on those previous examples. But now here you are wondering, there's nothing standing in front of them. So what should I now do? Listen, whenever you are seeing a reaction, an element standing alone or a compound, and there is no number standing in front of it, you are not to provide any number. You are not to provide. You understand? Because the reaction is already balanced. Don't go and write something else. Please take note. Whenever you are not seeing anything, you take it to be one. There is an invisible one you cannot see. There is an invisible one here. There's also an invisible one here. You cannot see them. Note it. There is an invisible one. So let's write. Take note, gases and aqueous species appear. So based on what I just said, KEQ will now be equal to, what's my formula? Product over reactant. This is my product. My products are 2. Write for them individually. The first product is H2. Write how it is. Write how it is. Don't go and write. You know, I told you it's an invisible one. Don't go and write the one. No, listen. You see what I'm talking about. Right, just pick it out. Pick the product which you've done, put it inside the bracket, and raise it to the power of the coefficient. There's an invisible one here. I'm telling you, whenever you don't say anything, there's one there. Raise it to the power. What's the power? You can see now 1. You can see we've explained for hydrogen gas. Let's go over to iodine gas. So basically, to go back to the next element with times, what times? And then moving over to iodine, it's going to be I2. All right, you pick it. Put it inside the bracket and raise it to the power of the coefficient, which you can see, and it is 1 as well. So here becomes 1, raised to the power of 1. We are done with the product. Let's go back to the reactant. Divided by your reactant. This is your reactant. Pick it. Don't go pick the number, pick it. So then it is HI. You don't pick the number standing in front. You only pick any number that is inside it. You understand? So for instance, here was 2, pick it. Let's say here was 2 here now. Pick everything. You understand? So now put it inside the bracket and raise it to the power of the coefficient. What's the coefficient in this case? 2. So you raise it to the power of what? 2. And this is the equilibrium constant expression for this reaction. It's very simple. I'm going to give you one practice question to master it very well. So let us get into your own practice question and move further to other practice examples under this aspect. So go over to another concept. Okay guys, here is your own practice example. All right, you should provide the KEQ for this reaction. You can see that they formed NH3. NH3 is called ammonia. This reaction in all has a name. It's called Haber's process. What's Haber's process? Haber's process is the process used to industrially produce ammonia, and there is a catalyst used. That catalyst is called finely divided ion. But I'm not talking about this. You should provide the KEQ based on what I've explained. Check their state. If they are gases or aqueous species, they will appear. So you put them based on what I've explained. The number standing in front of them should be raised as the power. We are good to go. Whenever you say number standing in front of an element in compound, take that number, take that thing to be 1. There's an invisible one there. So it is very easy. Let's go over to more practice example. Okay guys, moving further, let's get into this particular question. We should provide the KEQ for this reaction, which is called the equilibrium constant expression for this reaction, and it is very easy. But you should follow the rule. I told you, gases, aqueous species, both of them appear in the expression. But solids and liquids do not appear. So inspect, use your eyes to inspect and see the one that is gas and the one that is solid or aqueous or liquid. So in the case of this reaction, this is a gas, this is also a gas. This is a solid. I don't like solids because solids don't appear in this expression. I'm going to cancel it out. Like I told you, they don't appear. So write for what remains. So basically using a formula, product over reactant was my product. So write it, if you have one product, write for that only that one product. Bring it out, CO, put it inside the bracket, and the coefficient should be raised as a power of 2, divided by, all right, what's remaining? Oxygen gas. So O2, then put it inside the bracket, then raise to the, okay, there is no, okay, you know what is here? Here is 1. You understand? Raise the power of 1 because, there is an invisible one here. I told you when there is no number, there is an invisible one here. This is the answer to the question. Don't go and add this up because in the optional exams, they will just write it based on the general knowledge, and most persons, they will just pick that one. You must take note that solids, they don't appear in the expression. I believe it is clear. So we'll go over to more practice example. And the next one we're going into is your own. You solve the question and provide the answer in the comment section. Okay, guys, here is your own practice question. So you solve and provide the answer in the comment section. All right, this is how it works. Oh, okay, you are the one to solve it, not me. So provide the answer. And now, I know some persons might be wondering, how will I know that, okay, this is a solid, this is a gas? You'll be given the questions. You don't have to be scared, they are all simple. They will tell you that, okay, this is solid. So the one that is solid or liquid, cancel them out and write for the gases and aqueous species. For aqueous, I told you how to note them, you see AQ. So that's how it works. Let's progress to more practice examples. Okay, guys, let's get into this practice example. The reaction is balanced. There is no number, it's balanced. So all the coefficients are 1, 1, and 1 because I told you when there is no number, take it to be 1, there's 1. You get, and I told you how to write the KQ for a reaction. You always make sure that you check if the species is solid, liquid, gas, or aqueous. So solid and liquid, they don't appear. So basically, we're inspecting, and we saw that CaCO3, which is popularly called limestone, is a solid. I cancel it out. This one, which is CaO, which is popularly called quicklime, I cancel it out, is a solid. So the only thing remaining down is for carbon dioxide CO2, and it's the only species. So basically, when you find yourself in this particular type of question, and there's nothing remaining in your left hand side, you just write it straightforward. So basically, this is how it works. My product, I'm going to write for my product. My product is CO2. You understand? And you put it inside your bracket and raise to the power 1. You understand? So now I know you want to write for reactant. There is no reactant divided by what? Divided by nothing, because this is my reactant, there is nothing my reactant side. So because you want to say you're divided by 1 is still the same thing. So just remove it because there's no reactant, and this is the answer to the question. I believe it is clear. It is very simple. Okay, guys, moving further, here is your own practice question. So you solve this question and provide the answer in the comment section. So you can see how questions under this aspect are being tackled without stress. They are all very easy. So solve this question and provide the answer in the comment section. Moving further, let's get into this practice question on the board. Is still on writing the equilibrium constant expression for a reaction. So we are still asked to write the KQ for this reaction. So what do we do? Simple. It is product divided by reactant. Inspect to know your species. All right. This is AQ, aqueous species, and I told you that they appear when writing the equilibrium constant expression. This is AQ, and I told you they appear when writing the equilibrium constant expression for reaction. AQ, I called it aqueous. You get, here is it, and they appear. Now, this is H2O, and it is a liquid. What did I tell you about liquids? They don't appear. So I'll cancel it out. You get, and focus on the other, which is AQ, they appear. So let's write product divided by reactant. What are my products? The first of them is NH4 plus. Write it the way they gave it to you. Don't want to change anything. It is NH4 plus, write it like that. First of all, I told you put it in a bracket. We'll do that. And then go back to the next using dots to separate, which is times. The next is OH minus. Put it in a bracket as well. Divided by the only thing that will appear here, which is ammonia. NH3, alright, and also you put it in a bracket, alright. So basically, let's raise it to the power. For this one, it is 1, so raise to the power 1. You are not seeing anything, so you take it to be 1, you get now. Same applies to this other guy, you raise to the power 1, and same applies because the reaction is balanced, or I've checked it, the reaction is balanced, and also raise to the power here, and then it's still 1 for ammonia, and this is the equilibrium constant expression for this reaction. You can see how easy it is. It's very simple. Moving further, let's get into the next concept in this video lesson. And this concept is a principle called the CHATELIER'S principle. Don't worry, I'm going to explain everything you need to know on this principle, and as well solve so many practice questions on this principle and give you your own questions to solve and provide the answers in the comment section. Let's get straight into the principle.
Have more understanding about chemistry calculations and solving all of these type of questions. I already have them on the chemistry masterpiece, okay, which is calculations and keynotes in chemistry. So if you are preparing to write the JAM exam, this book is very, very important for you. Now, for more information getting the chemistry masterpiece, do well to direct message me via my WhatsApp number. It will be on the screen.
So, moving further, let's get straight into the CHATELIER'S principle. We have to know what it states. Listen carefully. Now, CHATELIER'S principle states that if an external constraint, please listen very well, this principle states that if an external constraint, alright, if an external constraint, listen, I'm going to explain what this means, but just take note of it. If an external constraint is imposed on a system. Now, when it comes to CHATELIER'S principle, the word system or the word reaction can be used interchangeably. Meaning that I can call a reaction a system, I can call a system a reaction. So what does this law state? It states that if an external constraint is imposed on a system or reaction at equilibrium. Now, before I state everything, just listen. I believe now you understand what I mean by a system or reaction being at equilibrium. This is what I mean. Let's say, for instance, A plus B reacted together to give rise to C plus D. What will you say about this reaction? Will you say this reaction is at equilibrium? Yes. You will say that. Why? You saw this sign called the reversibility sign. Let's say this reaction just existed like this. A plus B yielded C plus D. Can you say this reaction is at equilibrium? No, because it doesn't have a reversibility sign. I believe you understand. That is how it works. So we just said that CHATELIER'S principle states that if an external constraint is imposed on a system or on a reaction, this is the system at equilibrium. This system is at equilibrium. This system now will readjust itself to annul the effect of the constraint. That is what CHATELIER'S principle is all about. It states that if an external constraint is imposed on a system or imposed on a reaction at equilibrium, the reaction will adjust itself to annul the effect of the constraint, and I'll be explaining what I mean by all this. So listen carefully. So the question we ask ourselves, what are these constraints? Listen. What are these external constraints that can affect reactions at equilibrium? Here are these constraints. There are three of them. Alright, the first external constraint is simply what we call change in temperature. It's simply what we call a change in what? Temperature. We have another external constraint that must be noted, and that constraint is simply called change in pressure. Change in what? Pressure. And moving further, we have another external constraint which is simply called change in concentration. So all of these are the external constraints that can affect reactions at equilibrium, and I'll be explaining what I mean by all of these things. They are all very easy. So just listen carefully. Now, moving further, before we start talking about how all of these external constraints affect reactions at equilibrium, we have to take note of these, words. Now, please take note of this. Whenever we talk about CHATELIER'S principle, we always talk about this, and that is called equilibrium position. Please take note. We always talk about this, which is called what? Equilibrium position. Please take note, and I'm going to explain what I mean by equilibrium position. Just listen carefully. Now, moving further, this term equilibrium position can move to two different sides. This equilibrium position in a reaction, listen very well, can move in the right hand side, or we can say can shift to the right and as well shift to the left. Listen, equilibrium position in a reaction, because this is where we have to start explaining from. Equilibrium position in a reaction can actually shift to the right and as well, alright, shift to the right and as well shift to the left. You can see what I just said. This will help us a lot. Equilibrium position can shift to the right hand side of a reaction and also shift to the left. So I have to explain what I mean by when equilibrium position in a reaction shifts to the right and also when equilibrium position in a reaction shifts to the left. What do I mean by this? Because this alone is going to help us solve a lot of practice questions. So listen very well. Now, when we say equilibrium position in a reaction shifts to the right, it implies two things. And also, when we say equilibrium position in a reaction shifts to the left, it implies two things as well. When we say equilibrium position in a reaction shifts to the right, it means that, listen, it means that the forward reaction, of that particular reaction is favored. Take note. Please, I'm going to explain. I will solve, and we are going to solve a lot of practice questions. So listen. It means when we say it shift to the right, it means that the forward reaction of that reaction at equilibrium is favored. Because I believe you already know here that when we talk about chemical equilibrium, we talk about reversible reaction. And reversible reactions have two types of reaction in it. We have the forward reaction and as well the backward reaction. So I'm talking about the forward reaction now. When we say equilibrium position shifts to the right, it means that, oh, the forward reaction of this reaction is favored. And also, it also implies another thing. Like I said, it implies two things. Now, forward reaction always is the part of the reaction that has the product forward, backward. So now, since the forward reaction is favored, listen next. More of the product is formed. More of the product is formed. Take note of what I just said. It's very key. More of the product is formed. So when we say equilibrium position shift to the right in a reaction, it implies two things. The forward reaction is favored and more of our product is formed. Take note. But when we say equilibrium position shift to the left, it means two things as well, just opposite. So since this one forward reaction is favored, here will now be the backward reaction is favored. Alright, the backward reaction is favored. And in turn, what happens to the other point? I believe you know what will happen because this one is more of the product is formed. So what will be here? More of the reactant will be formed. Please take note. More of the reactant will be formed. Take note. It's very, very important. Will be formed. I believe you are following me. All these things are very, very important. Now, moving further, since we've gotten this point, with this point alone, let's answer some practice questions based on this point. Just listen, they are all very easy. Okay guys, moving over to the first question on equilibrium position. Here is the question. Let's read it together. I will solve this question. The next you will solve it and provide the answer in the comment section. Alright, so here is the question. It says, in the reaction below, this is the reaction and the reaction is balanced. Alright, the question now says, the equilibrium position in this reaction above shifted to the right. They now ask us the question, but we should take note of this word, equilibrium position shifted to the right. I've given you all what you have to know when equilibrium position in a reaction shifts to the right. What are the two things I told you? The forward reaction is favored, more of your products are formed. Put that in your mind. If the equilibrium position of that reaction shifted to the left, the backward reaction is favored and more of the reactants are formed. I believe you understand now. So moving further, what happens? Option A, more of NH3 is formed. Wow, NH3 is called ammonia. Where was NH3 found? NH3 was found in the forward direction. NH3 was the product and they told us it shifted to the right. Wow. It seems option A is correct because I told you when equilibrium position shift to the right, more of your products are formed and the forward reaction is forward. This is a forward and this is a backward reaction. You get. But let's read all other options. Option B, less of this is formed. No, it can't be this. Less of this can be formed when equilibrium position shifts to the right. I believe you understand because I told you when you shift to the right, more of your product are formed, the forward reaction is favored, and what's found in the product? NH3. So more of NH3 will be formed, not less of NH3 or even more of H2. More of hydrogen gas can be formed because equilibrium position shifted to the right. If it was equilibrium position shifting to the left, that's when more of this will be correct. I believe you understand. It is very easy. So the answer to this question becomes option A. You can see how it was tackled. It is very, very simple. So let's get into your own practice question. You solve it and provide the answer in the comment section. So move straight into all of those external constraints that affect reactions at equilibrium, explaining all of them one after the other. Okay guys, here is your own practice question. So you provide the answer in the comment section. It is very easy. Read your question, understand it very well, and go to your options and pick your answer. You can see here that it said equilibrium position shifted to the left, and I told you what happens when equilibrium position shifts to the left. What happens? The backward reaction is favored, and more of your reactants are formed. You understand? They can mention the reactant in the option you get, but I don't want to say much. You can answer it. Option A, more of SO3 was formed. I don't want to say much. Option B, more of reactant was formed. I don't want to say much. I believe you know the answer. The forward reaction is favored. I don't know. Alright, so you provide the answer in the comment section. They are all very easy. Now, if you find my video lesson helpful, make sure you click on the subscribe button to my channel and also share my lessons with your friends because it will help you all improve greatly. Let's move over to how those external constraints, which are change in temperature, change in pressure, and change in concentration, affect reactions at equilibrium. They are all very easy. Alright, so all of these we've learned, make sure you take note of them. So let's get into more concepts under this topic, chemical equilibrium. Okay guys, moving further, let's now talk about those external constraints that affect reactions at equilibrium. So first, I'll be talking about the first external constraint, and that constraint is simply called, alright, we talked about it initially. That constraint I'm talking about first is simply called change in temperature. So listen very well to the way I'll be analyzing this aspect and as well as solving so many practice questions under this external constraint, how it can affect a reaction at equilibrium, and then give you your practice questions so you can master this aspect. They are all very easy. So first of all, this is how we start. In chemistry, or in science generally, reactions that are influenced by light, those reactions, we call them photochemical reactions. We have other reactions that are influenced by heat. Listen, we have some other reactions that are influenced by heat. What brought about those heats? It is temperature. So, on changing temperature, we'll be talking about reactions that are influenced by heat, and those reactions are simply what we call thermal reactions. Listen, they are called thermal reactions. These reactions can be divided into two aspects on this context. All right, we have two. We have what we call the endothermic reaction. Listen carefully. We have what we call the endothermic reaction. All right. And as well, we have what we call the exothermic reaction. And I'll be explaining to you the difference between this reaction and also using them to explain how change in temperature can affect reactions at equilibrium. So listen very well. So the question you ask yourself, what is an endothermic reaction? An endothermic reaction is a reaction in which heat is absorbed. Are you there? But for exo, heat is given off to the surrounding. Please listen very well. Remember I told you that it is temperature that brings about the heat. And this, I told you, in reactions that are influenced by heat, they are called thermal reactions, and there are two types. We have endothermic reactions and exothermic reactions. Now, basically, this heat I am talking about, listen, because it is this heat that brings about this thermal reaction. Now, this must be noted. The heat content of a reaction is called a term. That term is simply what we call enthalpy. Take note. The heat content of a reaction, what's it called? Enthalpy. And you must know here that enthalpy is symbolized as H. As we are having enthalpy, so we are having another term called change in enthalpy, because we need this thing to analyze an endothermic reaction and also an exothermic reaction. We need what I'm about saying to know if a reaction is endothermic or exothermic. I'm going to explain again. Just listen. So as we're having enthalpy, so we're having what we call what? Change in enthalpy. So basically, I believe you know here that in science, change is symbolized as this. And enthalpy, we already know that is symbolized as H. So change in enthalpy will become delta H, because it is the delta H sign we use to determine if a reaction is endothermic or exothermic. Now listen, if this sign can be either be positive or negative, I beg you take note. If the change in enthalpy of a reaction is positive, we simply say that reaction is endothermic. I beg you, take note of what I am saying. They are very, very important. So basically, the heat content of endothermic reaction, they are always positive. The change in enthalpy is always what? Positive for endothermic reaction. So moving over to exothermic reaction, the change in enthalpy is simply what? Negative. We need this a lot. We need this to be able to understand this aspect. So let me take it again. So I've said here that, what brought about, heat? It is temperature. You understand? And reactions that are influenced by heat, they are thermal reactions. Thermal reactions on this context can be either endothermic reaction or exothermic reaction. And then I told you that the heat content of any reaction in chemistry, it is defined as enthalpy. And this enthalpy is symbolized as H. As we're having enthalpy, so we're having change in enthalpy. So change in enthalpy will now be change in H, delta H. This sign is symbolized as delta H and is of two types, two signs. It can be positive or negative. If delta H is positive, we simply say the reaction is endothermic. If delta H is negative, we simply say the reaction is what? Exothermic. So all this must be noted. I believe now you've understood this aspect on that change in temperature, because we'll be analyzing some concepts now. Okay guys, moving further, based on what we've said, on that change in temperature now, we have two reactions that must be noted: endothermic reaction and exothermic reaction. What did I tell you for endothermic reaction? What's the delta H? What's the enthalpy change? For endothermic reaction, it is positive. What about the enthalpy change for exothermic reaction? It is what? Negative. Now, please take note, because on change in temperature, not just change in temperature, when we get to explaining change in pressure and change in concentration, how they can affect a reaction at equilibrium, we will not be using the term increase and decrease. Now, listen. For endo, I am interested now in endothermic reaction. Leave this alone and talk about endo. Now listen. Now listen how I'm going to analyze it. If now there are 2 points you must take note here. Listen. Increase and decrease of something. What are we increasing and decreasing? Temperature. So listen. Increase. Listen to this first point on endothermic reaction. Increase in temperature. I beg you, take note. Increase in temperature for an endothermic reaction listen, favors the forward reaction. Favors what? The forward reaction. Let's write out a reaction. Let's say, for instance, A reacted with B to give me C plus D. And I believe you already know this is the forward and this is the backward. You understand? So when we increase it, now let's say, for instance, the delta H of this reaction is positive. So you can see that this is a reaction at equilibrium and delta H is positive, telling us that it is endothermic. So for instance, in this reaction, we increase temperature. What happens? It should favor the forward reaction. And what are the forward reaction makeup? C and D are the forward reaction. So it should favor what? The forward. And I believe, you know what, when the forward reaction is favored, what does that imply? It means that more of the product will be formed, more of C and D will be formed. You understand? When you increase temperature and it favors the forward, in this case, the forward reaction is favored, meaning that more of C and D are formed whenever you increase temperature. But what happens when you decrease temperature? What happens when you decrease temperature? Please take note. Decrease in temperature, it is the opposite. All right, it favors the backward reaction. So for any reaction that is endothermic, when you decrease temperature, it favors the what? Backward reaction. So in this case, more of A and B will be formed. See, all these things are very simple. Based on this, we will solve practice questions. So listen carefully. So I've analyzed for endothermic reaction. Let's go over to analyze exothermic reaction and as well solve practice question based on this aspect and move over to the other external constraint, which is changing concentration and change in pressure. So here is for an exothermic reaction. Let's say, for instance, A, B again reacted to give me C plus D. But in this case, delta H, enthalpy change is negative. All right, positive plus VE, negative minus VE. That's how we denote positive and negative. Plus VE and minus VE. So now let's increase and decrease temperature now. Increase, all right, we increase temperature, and also here, we are going to decrease temperature. So increase in temperature, what happens? For an exothermic reaction, it is actually the opposite of what is happening here. That happens here, opposite. So here, for exo, when you increase temperature, what's the opposite? The backward reaction is favored. Wow. When you increase temperature, the backward, please listen very well. The backward reaction, all right, is favored, or we can simply say favors the backward reaction. Anyhow we say it, it's still the same message is passing. So here, decrease in temperature will not be opposite of the decrease we have here. So in decrease temperature, the forward reaction is favored. I believe you understand. Please look at it very well. Here, you increase temperature favors the forward. Here now, because it's exo, heat is giving up to the surrounding. When you increase temperature, the backward A and B more will be formed. Same now for D. Now for the other, which is decreased temperature, the forward reaction is favored. When you now decrease temperature for exothermic, the forward is favored. So more of C and D will be formed. I believe you understand because I'm about solving questions. I'll solve the first one, I'll give you all to practice. We'll go back to the next external constraint and learn how it can affect a reaction at equilibrium. It's very simple. Okay guys, let's get straight into this first practice question. After analyzing this question, I'll give you on to analyze. So listen carefully. You can see that they gave us a reaction and they gave us the delta H. They told us that the delta H is negatively charged. Listen, it is minus. Are you there? We should take note of that. If delta H is minus, it tells that, oh, that reaction is exothermic. So you have to know all the things that apply to temperature being increased and decreased for exothermic reaction. I've told you that. What did I tell you? Increase in temperature for exothermic reaction. Where does it favor? When you increase temperature for exothermic reaction, it favors backward. But when you decrease it for exothermic reaction, it favors forward. So basically, you've seen the answer already. This is the forward reaction. Because more of SO3 will be formed. I've already explained to you when a forward or backward reaction is favored, it means that more of that thing in the forward reaction is formed or produced. So option A is the answer, not more of O2. This one, because I told you, whenever temperature is decreased, it favors the forward. What was found in the forward? SO3. So more of SO3 will be formed. You understand? You can't favor more of these two guys to be formed. That's why B and C, they are wrong. The answer to this question is option A. It's very simple. It is not difficult. So that's how it works. So get ready for your own practice question. So this time around, I'm going to change the word. Here was decreased before, so it now be increased. So this is your own question. Please, when you are providing answers to this question, signify the question you're solving. So we'll know exactly if you are getting it correctly. Definitely you are supposed to get it correctly. They are all simple. You understand? So I've increased is increased. I've increased temperature for exo. What will not happen? I don't know. I've told you already. Relax. Let me change the option. So option A, let me write here to be. Okay, let me leave here like this. More of SO3 will be formed. All right. Option B, more of O2 will be formed. That's okay. Option C, let me remove it and put something like the forward reaction is favored. Let me see how smart you are. The forward reaction is favored. Is favored. These questions are very simple. Analyze it. Is exo the increased temperature? What did I tell you when you increase temperature for exo? The backward is favored. So you look for the thing that is found in the backward and then answer the question. It's very simple. I'm waiting for your answer. Provide answer to this question. So you can see how we've analyzed how to solve questions on change in temperature being an external constraint that affect reactions at equilibrium. Let's go over to the next external constraint, and what we'll be talking about next is change in pressure. Now, let's get into the other external constraint that affects reactions at equilibrium. Now, this external constraint applies to gases only. They can ask you the external constraint under the Chatelier's principle that applies to gases only is what? The change in pressure. And I'll be explaining to you how it works. Now, listen. Now, listen very well. Now, this is a reaction at equilibrium. Let me just write the proper reaction, and it will be formation of ammonia, NH2, N2 plus H2 to give me, listen very well, with this sign to give me NH3. Let me balance it. I'll put 2 here. All right. I'll put 3 here. All right. It's okay. It's okay. It's balanced now because here is 2, here is 2, here is 6. 3 times 2, 6, and here is 6. If you don't know how to balance reactions, and I believe from all of these things we'll be doing since, you've gotten a concept. But go watch my full video lesson on how to balance chemical reactions. They are all very easy. Now, listen very well. You know, on this aspect, we always talk about when you increase it, when you decrease it. So basically, listen. Increase, listen. Increase in, listen. Increase in pressure. Listen, no. Increase in pressure, all right, favors, and we explain. Let me write that. Let me just quickly write for decrease. So next, decrease in pressure, because we are talking about pressure now. Increase in pressure favors. So how do we know? How do we know? They're all very simple. Let me just tell you. When it comes to pressure, though there's something I have to like use to explain, which is Boyle's law, but I'll just explain it in a way that you'll be able to catch it. Now, whenever in a reaction, now the reason I said that it's talk about gases only because the species we're interested in are all gases. Don't worry, I'm going to tell you some things, but just take note of what we are doing. Just take note. Just take note. Listen very well. Let me explain what you need to know first. Now, increase in pressure favors the reaction side. We have two sides in a reaction, the right hand side and the left hand side, the forward side and the backward side, the product side and the reactant side. These are the sides. So whenever you increase pressure, it favors the reaction side with the lesser number of moles, or we simply say favors the reaction side with the lesser volume. Relax, I will explain how all of this works. So let me write, increase in pressure favors the reaction side with lesser volume. We can use volume, lesser volume, or we simply say lesser number of moles. Listen, and we explain, just watch. Here now, we are decreasing pressure. It's now the opposite. Decreasing pressure favors the reaction side with larger volume, or we simply say larger or we simply say larger number of moles. How do you know the side of a reaction with larger volume or lesser volume? Very simple. We just go over to add all their coefficients, all those numbers standing in front of them, add them together. So you can see this is my left hand side, this is the reactant side. So let's just take note of this now. This is the reactant side of this reaction, whereby this is the product side of this reaction. I believe you are following me. So basically, what are the volume here? What's the volume here or the moles found in this side? I told you, just add the number standing in front of the element. Remember, I told you, whenever you not see any number standing in front of an element, take it to be 1. So there is an invisible one here. We write it out. So basically, what's the volume here? It's called volume in this context, or moles. So here we simply call it. So here is simply called 1 volume. You understand? 1V. Let me write it in full. 1 volume. Here, what's the volume here? 3 volume or 3 moles. That's how it works. Listen. Here, we are only having one substance in the product side. And what is it? It is just 2 volume. So basically, in your product side in general, how many volume are you having? 2 volume. So everything in your product side is 2 volume. So here is it. Product is equal to 2 volume. Listen, oh, and reactant altogether 1 plus 3. All right, for reactant, it is 1 volume, all right, plus 3 volume. Altogether, what are we having? 4 volume. You understand? So, if you observe what is happening, in the reactant side, we have 4 volume in general. 1 plus 3, 4. In the product side, we have 2. So, the question cannot come in this way. In your question, they will not say increase. Let's say, for instance, the question talks about increase in temperature. Which side will it favor? Increase in temperature. Increase. Which side will it favor? It will favor the side with the lesser number of moles. With the what? Lesser number of moles or lesser volume. So what's the side with the lesser volume or lesser number of moles? Tell me, it is the product side. So your options again, they'll see right. Option A, NH3 will be produced more. More NH3 will be produced. That will be the answer based on the context of the question. But now, for instance, they said decrease in pressure, then the answer will be either the reactant side in general, but they can just pick one of the reactant like a nitrogen gas. They say more of nitrogen gas is formed, you are correct. Or they say more of hydrogen gas is correct, that's still correct. But they cannot put option A, more of nitrogen will be formed. Option B, more of hydrogen will be formed. They can't put those two because both of them are the answer to the question. Hope you understand what is happening. They are all very easy. They are not difficult. It's best to understand how all of this works. Okay, guys, let's move over to more practice examples under how change in pressure will affect a reaction at equilibrium. So listen carefully. Now, there is something vital I have to tell you, because this change in pressure, which is one external constraint that affects reactions at equilibrium, works under a law, under the gas law called the Boyle's law. Please listen very well. So if you are finding it difficult to understand gas laws in general, I already have a full video lesson here on my channel that explains on everything you have to know about the gas law. So after watching this lesson, make sure you go watch that full video lesson on my channel. So now let's get into understanding how Boyle's law affects to this aspect of chemical equilibrium. Now listen very well. I believe you know here that in Boyle's law, it states that volume of a given mass of gas is inversely proportional to pressure. Now let me just summarize what that law says. Listen, let's say we have volume and as well we have pressure. Are you there? Now, when something is inversely proportional, because I just said that for Boyle's law, volume of a gas is inversely proportional to what? Pressure. So what that tells us is whenever volume of a particular gas increases, for example, let's say this volume increases, what then happens to the pressure? Since it's inversely proportional, then it is going to decrease. I believe you are following me. Because for inverse proportionality, It talks about one increasing and the other decreasing. Let's say, for example, it is direct proportionality. It will be if volume increase, pressure will definitely increase as well. Now, why am I saying all this? It will help us understand properly how change in pressure can affect reactions at what? Equilibrium. Because I believe you know I've already given you the concept about how change in pressure can affect reactions at equilibrium. And what did I tell you? I told you here that whenever there is an increase in pressure, now leave this alone first, I'll come to it. But listen, let's get that straight again. Whenever there is an increase in pressure, which side of the reaction does it favor? It favors this. I told you this. It favors the side with the lesser number of moles or lesser volume. Look how I just said. I said when there is an increase in pressure, it favors the side with the lesser number of moles or lesser volume. Because you know me having this relationship, I can also form another relationship that says volume and pressure again. Now, there was increase and decrease. So let's say here was decrease. What becomes here will be increase. See, I believe you understand now because I'm trying to relate how Boyle's law affects this concept. In this aspect, there was increase in volume. What will happen to pressure? Decrease. Here there was decrease in volume. What will happen to pressure now? Increase. And what did I tell you initially about how pressure affects reactions at equilibrium? I told you that whenever there is an increase in pressure, it favors the side of the reaction. Remember, reactions have two sides. It favors the side of the reaction with lesser volume or lesser number of moles. I believe now you can understand perfectly what I told you. So listen very well because they might give you the question in different pattern. So it's best you understand and know perfectly what to do to solve any questions under this aspect, and they are very easy. That's why I brought out so many other examples to practice with. Now listen very well. This is the pattern to which I want to ask this question. Now, listen, I want to ask you a question on this. Let's play with it together. Now, this question, they gave us a reaction. Listen. Because sometimes they will not say increase in pressure favors what? They can just use volume. They can use volume instead. Now, let's say, for instance, in this particular reaction, they just said something. Let's work with this first up part. Now, the way I'm going to ask the question is based on volume. Now, not pressure anymore. I'm just teaching you the extreme way they can bring questions on. But most times, they'll bring it based on pressure. But this time around, let's say they are asking it in volume concept. And for this question, they now said something. They now said increase, listen, increase in volume. Increase in volume favors which side of the reaction? That's the question. So when you see questions that they not brought out volume instead of pressure you used to know, then you have to try to relate how volume and pressure are related together. And I believe you know that whenever volume increase, what will happen to pressure? Pressure will decrease. Do you understand? So when you see that, your mind will just go, oh, okay, if there is an increase in volume, definitely there will be a decrease in pressure. So you yourself just change the format of the question. So this question, which is increase volume, just change it to decrease in pressure. That's the best way to answer questions on this aspect. They are all simple. So you now answer the question based on decrease in pressure because literally both of them are related. You understand? Because it is the decrease in pressure that will be easy for you to get your answer. And I've given you the concept about how pressure affects reactions at equilibrium. Initially, I told you increase in pressure favors the side with lesser number of moles or lesser volume, and decrease in pressure favors the side with larger volume. You understand now? You understand? You can see decrease in pressure favors the side with larger volume. So there, let's analyze this reaction. It's not hard. So let's calculate the volume. You know this volume can also be called moles. You get, but based on what we have one volume, we have a 3 volume in the left hand side. Altogether is going to form what? 4 volume. And here we have 1 volume and another 1 volume. You must ensure the reaction is balanced. So altogether we have 2 volumes. So what then will happen? Now let's go back to the question again. The question says decrease in pressure. What did I tell you when you decrease pressure? It favors the side with the larger volume. Decrease pressure favors the side with the larger volume. Wow. So which side of this reaction will be favored whenever we decrease pressure? Favors the side with the larger volume. It's going to favor this side because here is 4 volume or 4 moles. Is it clear? It's very simple. It is not difficult at all. You get how it works. So I want to ask you a question based on this same so the way you now interpret it is not like favors the side with larger volume or favors the backward. I told this favors the what backward reaction whenever we decrease pressure. So let's say for instance I'm changing the format of the question, and now I'm changing the format of the question using volume concept. So here that was what do you call it? Let me write this way. Decrease in volume. Yes. Now I'm decreasing volume. Please answer this question. Decrease in volume. What side of this reaction, this same reaction, will it favor? So I think this question is question number 2, based on under change in pressure. Or this will be number 3, this will be number 4, so that we can be able to write out the answers in the comment section. Write your answer correctly. Don't rush. Take it step by step. You understand? I've given you so many questions. So basically, listen very well. So this same question, we are decreasing volume, then relate it to height affects to pressure, and use pressure concept to answer the question. It's very simple. So now let's get straight to the next question, which is this. Now let me just tell you something very important. First of all, I have to solve the question. Let me bring a question based on this reaction. Now for this reaction, the question is this. Let me just use pressure, you understand, so that we quickly tackle it. So let's say increase in pressure for this question 3. Increase in pressure favors which side? Is it the forward or backward? So let's understand it together. What's the rule I gave to you? First of all, quickly calculate your volume you get. For each of them, here is 1V, another 1V. You can call it mole as well. And this is 2 volume. So here is 2 volume altogether. 1 plus 1 is 2. And here is 2 altogether. So then I said increase in pressure. Now let me just tell you something very important. Normally, what's the concept about increase in pressure? When you increase pressure, what then happens to your volume? It favors the side with the lesser volume. Now, if you check this reaction, are you not seeing that both of them have equal volumes? Please note this. When you encounter this condition, please, change in pressure does not affect a reaction that has equal numbers of volumes at both sides. So basically, the answer to this question will be no change will occur because they have equal volumes or equal numbers of moles. Is that clear? It's very simple. It's not difficult. So basically, let's get back to this question. This is question number 4. And in this question, you'll be the one to solve it, because this one they don't have. Here is 2 volume and here is 1 volume. And here is my question now. Increase in volume. Increase in volume, what happens to this question? Please answer this question yourself. I told you, whenever you see increase in volume, try to change it in your head quickly to pressure format. So when there is increase in volume, what then happens to pressure? Decrease in pressure. So this question is decrease in pressure. So decrease in pressure will not favor what side? Is it forward or backward? Tell me in the comment section. It is very simple. So let's get more practice questions on that change in pressure. They are all very simple. Okay guys, let's get straight into this question. It's still under change in pressure. So here is the question. Let me tell you the question. So in this question, let's say the question says increase in pressure. Increase in pressure will favor which side of this reaction? Is it the forward or backward? That's what the question says. So what do we do? It's very simple. Now I have to tell you something. I told you this initially when we started. I told you that for change in pressure, being an external constraint that affects reactions at equilibrium, it only deals with gases. It does not have any business with solid species. So whenever, listen, change in pressure only deals with gases. So whenever you are giving a reaction, you first of all inspect and look for the ones that are solids. You understand? And when you see that, cancel it out. And what's the law? Quickly get your volumes. Since there is no number here, it is 1 for sure. So here is 1 volume and here is 2 volume. You can see this is the only species remaining because we don't have any business with carbon being solid. You guess. So moving further, what do we do? Increase in pressure. What's the law? When you increase pressure, it favors the side with the lesser volume. It favors the side with what? The lesser volume. So hence, in this question, the backward reaction is favored. Hope you understand. The backward reaction is what? Favored. You get. So what does this tells us? It tells us that more of oxygen gas will be formed. I've given you all the scenarios before. So that's how it works. It's very simple. It is not difficult at all. So get ready for your own practice question. This is question number 5. I solved it. I'll give you another question number 6. So you should solve it based on change in pressure. Okay, guys, here is your own practice question. When you decrease pressure in this reaction at equilibrium, what then happens? That's the question. First of all, cancel out things that should not be here. And what did I tell you that should not be here? Solid species. Cancel it out. So after that, you now get what you have left, and then you look at the question: decrease in pressure favors what side? That's the question. Is it the forward or backward? So when if you are telling me backward or forward, tell me what is formed or what is favored. Tell me what more is formed. You understand? That's the question. It's very simple. And this is question number 6, and it is for you. So we've come to the end on how change in pressure can affect reactions at equilibrium. They are all very simple. If you find my video lesson helpful, make sure you click on the subscribe button to my channel. Make sure you share this video. Make sure you give this video a like. You can't just watch without liking, without subscribing, because it's going to help you and help your friends as well. So let's go over some more concepts under this aspect of chemistry. Now you can see we've gotten to the next and the last external constraint, which is change in concentration. I'll just give you what you need to know. Listen very well. Concentration is a broad term, but I will just tell you what you need to know that pertains to the topic chemical equilibrium. Let's form a reaction at equilibrium A plus B now, in using the reversibility sign giving me C plus D. Now, there are various criteria to which a question can come. I'll be giving us 4 criteria. So based on these criteria, we'll be solving questions. Just relax and listen. This is how it works. I said I'll be giving us 4 scenarios. So the first scenario will be addition. Listen. Addition of products. Please listen. In a reactor we have 2 sides. This is the product and this is the reactant side. So in the first case to which a question can come, we'll solve question. You relax. The first one is addition of product. Means that, okay, in this case, I am adding more of my product. What happens to the reaction? What side, what equilibrium position will that reaction go into when I add more to my products? Listen, addition of product favors the reactant side. I beg you, take note. Whenever you add more to your product, it favors your reactant side. Note it. We'll solve question. Another point. All right. Another point will be addition. Another addition now. Addition of reactant. So in this case, I am adding more to my reactant. I'm adding more to this. I'm adding more to the reactant. What happens? When you add more to your reactant or add more to your product, it favors the other one. So in this case, I'm adding more to my reactant. It should favor my product side. So then favors the product side of the reaction. These are the 2 first cases. Let's go over to another case. Listen, they are all very easy. We'll solve question. So you just relax. Question, another point. Now, the points I'll be talking about will be removal of product. Then I tend to remove more of my products. It favors my products. That's how it works. Removal of product favors the product side. All of these things will help us solve questions. So note it, and it's very important. Another point. Since I removed from my product, then I'll remove reactant. Removal of reactant, all right, favors what? Reactant side. Favors the reactant side. I believe you've gotten the point. Don't worry. To understand and appreciate it more, we'll solve questions on that change in concentration, and they are all very easy. You just relax and get ready for the questions under this aspect. So we'll move over to more concept under this aspect of chemistry. Okay guys, let's get into this question. It's very simple on change in concentration. This is the first practice question. After solving this, I'll give you your own to solve. They are all very easy. Let's tackle it together. Here is a reaction at equilibrium. All right, you can see arrow and S forms the product. P and Q forms the reactant. This product side or forward reaction side, you understand those things now. And this is the backward reaction and as well as the reactant side. So the question is, which of the following will increase the yield of arrow? Wow. Which of the following will increase the yield of arrow? Where was arrow found? Product side. So in general, which of the following will form more of our product? Because arrow was in the product. So take note of all those points I gave to you. So without even checking the option, let's think together. Now listen. For us, because now arrow was in the arrow, they said which of the following will increase means that will favor. You understand? Will favor more of our product because arrow was in the product. Hope you are getting the picture. It's not hard. So which of the following will increase more, will increase the yield of arrow? Which of the following will increase the third reaction? Will increase the product side. What did I tell you? You remove. When you remove from your product is formed. But when you add to your product, it favors your reactant. I told you these things now. They are not hard. They are not hard. Just relax. When you remove from your products, it favors your product. When you remove from your reactant, it favors your reactant. I told you these things. When you add to your product, it favors your reactant. When you add to your reactant, it favors the product. All right. So basically, removing some S. Yes. When you remove, listen. When you remove some part of your product, because S was in product. I told you when you remove your product, it favors your product. That's the answer. Take note, if the reaction occurs in a larger vessel, it does not affect anything. It does not affect arrow to be formed more. I did not tell you that. So don't take note of that. It's not important here. And also adding a catalyst, did I tell you? Now, you must take note here that catalyst does not affect the equilibrium position of reactions. Catalysts only speed up the rate of the reaction and they themselves remain unchanged at the end of the reaction. Option D, addition of some S. Is that what I told you? But I told you when you add to your product, it favors here now. And the question is saying we should make sure we increase the yield of our product, which is arrow in this case. So we must remove from our product. Removing S will form of arrow. I told you these things. They are all simple. So A is the answer. They are all very easy. Here's your practice question. Let's try to, take it smartly. All right. Which of the following will increase? Here is the question. Which of the following will decrease? They are not hard. You just have to think and don't rush it. Will decrease the yield of arrow. All right. Will decrease the yield of arrow. So here will be removal, all right, of some, or let's say P. So when you remove P, what happens? But take note of your question. Which of them will decrease the yield of arrow? So for we to form less of arrow, what do we do? That's the question. You understand? You know it. You can answer it. I believe in you that you can answer the question. So do it. And I'm waiting for your answers. All right. So you can see how questions under this aspect are being tackled without stress. All right. So let's move over. You can see we've tackled questions under Le Chatelier's principle. So with all of this knowledge you've gotten, go practice more questions. They are all very simple. All right. Let's move further into more concepts under chemical equilibrium.
To have more understanding about chemistry calculations and solving all of these type of questions, I already have them on the chemistry masterpiece, okay, which is calculations and keynotes in chemistry. So if you are preparing to write the JAM exam, this book is very, very important for you. Now, for more information getting the chemistry masterpiece, do well to direct message me via my WhatsApp number. It will be on the screen.
Now, this must be noted. Please listen very well. I've actually formed the foundation initially when we started. Remember, I believe you are very familiar with what KQ means, which is the equilibrium constant expression for a reaction. Now, KQ are of two types. I told you initially. Oh, I told you, but I did not tell you them. Like, I did not tell you what they are. Now, KQ can be either KC or KP. Now, the question you ask yourself, what's KC and what's KP? KC simply means, remember, KQ simply means equilibrium constant expression. But KC means now equilibrium constant expression written in terms of concentration. Equilibrium constant expression written in terms of what? Concentration. Equilibrium constant expression written in terms of what? Concentration. Note it. It is the equilibrium constant expression written in the terms of what? Concentration. But what does Kp mean? Simple. It is equilibrium constant expression written in terms of partial pressure. Please take note of it. It is equilibrium constant expression written in terms of partial pressure. Now, let me give you an example of what I mean by this, because in a question can come and will tell you, write the Kc for this reaction and then write the Kp. It's still the same principle, but there's just slight difference between them, and I'll be showing you the difference. Now, let's focus on those reactions we're already familiar with, and I'll be bringing this reaction NO2, which is a gas, then to give me what now? N2O4, which is also a gas as well. I have to balance it by putting 2 here. All right, we are okay. The reaction is balanced. So now, here is the Kc, and let's write the Kp together. You understand? Kc and Kp, how does it work? It's same answer, but just different representation. So let's do for Kc first. So here is how it works. Listen. For Kc, I believe you already know that it's product of a reactant. This is your product. Then write it down, N2O4. You put now Kc. Concentration in chemistry simply means brackets. So those things we're writing is literally Kc. On specifying, it is Kc we've been writing, but we still can call it Kq because they are all part of Kq. But basically, you should understand here that whenever you're writing Kc, they should be in form of concentration. All those species should be inside the bracket, and the bracket should be written like this. Like this, you understand? And we must raise it at the power you get. You understand? Then divided by, you do for this as well. So then you write it NO2, open a bracket, the same pattern. When I divide it by Kp, you see the difference. So Kp will now be raised to the power, which is 2. So this is the Kc of this reaction. It's still the same as Kp. It's still the same as Kq, but Kp, little difference. Don't worry, I will explain. So moving over to Kp, this is how it works. Kp is still the same approach. It's still product of a reactant, but this is how it works. I beg you, listen. Product over reactants. Now, my product is N2O4, but now we don't use this bracket for Kp. We use this bracket. Hope you are following me. This is the bracket we use, but this one we use like a block, you get. And now we simply write P in front of it, like something like P like this. Hope you are following. This P signifies that it is actually Kp you are writing for, and that P is partial pressure. Relax, they are all simple. Then you still raise it to the power here. You understand? Divided by your reactant, which is this NO2, this type of bracket. All right, have to bring it out a little, so we can have space for this, our P like this, and then raise it to the power. So this Kp, this Kc, the same answer, but different representation. I hope it's clear how it works. They are all very easy. So guys, you can see how we've tackled so many aspects under this topic. If you find my video lesson helpful, make sure you click on the subscribe button to my channel and also share my lessons to your friends. All right, let's move further into other concepts. Now, this time around, we'll be solving questions that pertain to getting Kc of a reaction and as well as getting Kp. They are all simple. You just relax and I will explain. So let's solve a question that require us to get Kc. You now see the importance of all of these formulas we are getting. You now see the importance of all of this representation we are getting. But for O-level exams, ordinary level exams, if you're in a country like Nigeria, Ghana, African country, even if you are from America, Indian, and you are in your high school and also colleges, those persons in 100 level, like first year, they most times stop at this level. But now, the questions that we're about solving are questions that pertains to higher level, like in Nigeria, they call it A-level, advanced level, like 100 level student, 200 level student, like that. First year in sciences, second year students that are major in chemistry will be solving questions that pertain to you guys now, so you guys should get ready.
To have more understanding about chemistry calculations and solving all of these type of questions, I already have them on the chemistry masterpiece, okay, which is calculations and keynotes in chemistry. So if you are preparing to write the JAM exam, this book is very, very important for you. Now, for more information getting the chemistry masterpiece, do well to direct message me via my WhatsApp number. It will be on the screen.
Okay, guys, let's get straight into this question. It's very simple. All right, they told us nitrogen reacted with chlorine to produce nitrogen trichloride. That's a reaction. Nitrogen, all right, reacted with chlorine. Listen, don't just write nitrogen as N like this. So nitrogen is a diatomic gas, meaning that it's supposed to be N2. Even if you can say from the question now, they wrote nitrogen as N2. reacting with chlorine. All these things are gases, and most of the time they are diatomic. All right, chlorine gas. You can see here it's CL2. To now give the reactions at equilibrium must do this. To now give us nitrogen trichloride, meaning NCl3, you get. But we have to make sure that the reaction is balanced. It's best I put 2 here. If I do that, my chlorine will not be 6. 2 times 3 will not be 6. So I'll put 3 here. 3 times 2, chlorine will not be 6, balanced. And nitrogen is already 2 here, and nitrogen is 2, is balanced. It's simple. So they are asking us to get the Kc. How do we get Kc? They gave us all the concentration of the species, and they are all gases. That means they will appear in the expression you get. So let's simply write the Kc for this reaction. They are all very easy, and it is product over reactant. This is my product, and it is NCl3 open bracket close bracket raised to the power of 2 divided by reactant. Let's write for this one first. N2 open bracket close bracket raised to the power of 1. You get now, because there is nothing, so you take it to be 1. We said this many times. All right, times for this, which is Cl2 open bracket close bracket raised to the power of 3. You get. So we've gotten the Kc expression. Let's impute all of the parameters into the expression to get our Kc for the reaction, and all of these things are very simple. So what do we simply do? It's very simple. Kc will now be, what's the concentration of our product? All right, it was given to be 0.5 molar. So there's no need to write the units. Now, basically, we have to understand something. We have to understand here that this capital letter M is simply called molar. All right, and molar is, see, this M can also be represented as moles. Listen, mole slash dm3. You understand? So molar, mole per dm3, they are literally the same. You get. So in some other questions, you might not see capital letter M and you see mole per dm3, it's still the same information. You get. So raised to the power 2, based on our expression, we've done that, divided by the concentration of our reactant. For nitrogen, it was 0.15. You have to be careful, don't make mistakes. 0.15. All right, open the bracket, close the bracket. All raised power of, there's 1 now, there's invisible one, just do that. You get times. All right, for chlorine, it was given to be 0. All right, you do that. So it's 0.25, and all raised to the power of what? 3. You get now all raised to the power of 3, and then we'll do that. So let's impute all of them in our calculator to get our Kc. So what becomes the Kc? It now becomes 0.5. All right, open bracket, close bracket, all raised to the power of 2. Down now, 0.15. All right, all raised to the power of 3. Let's say our Kc value. Wow. So the answer to this question becomes 106.67, and it doesn't have any units, and this is the Kc for this question, and it is very simple. So get ready for your own practice question. So here's your own practice question. So you solve and provide the answer in the comment section. You can see it's between sulfur dioxide reacting with oxygen gas. So it's best I give you the reaction so you can get the correct expression to solve inside. So sulfur dioxide, O2 di, reacted with oxygen gas to give me SO3, balancing it, putting 2 here, and as well putting 2 here. Hence, the reaction is balanced. So provide the Kc and then the expression, and then calculate the Kc. You get. That's what you have to do. It's very simple. Get ready for more practice example. Okay, guys, this is another practice example. This is actually question 3. The one I gave to you previously is question 2. The one I solved was question 1. So I've given you 2 questions under solving questions that pertaining to you putting values into the expression. So if you are providing the answers in the comment section, you highlight your question and the answer, so we know exactly what you are doing. I can follow through all the comments you get. So that's how all these are solved. They are all very easy. Let's get into more concepts under chemical equilibrium, and this time around we'll be relating Kp and Kc together. There is a formula that relates them together, and there are practice questions that you may likely see under those aspects. So watch closely and listen carefully. Okay guys, listen carefully. There is a formula that actually relates Kp and Kc together. Though that formula can be derived, but it's best for you to just know the formula that relates them. And the formula is simply Kp is equal to Kc, open bracket, RT, close bracket, all raised to the power of change in number of moles of the species in the reaction. I will explain. Just listen. So first of all, it's important for me to tell you what all the parameters mean. I believe you already know what Kp means and as well what Kc is. Kp is equilibrium constant rating in terms of partial pressure. So the answer of Kp will be expressed in pressure. And most of the units to which Kp is expressed is atm. Don't worry, I will explain. Kc is equilibrium constant rating in terms of concentration, whereby Rho is called the molar gas constant. Molar gas constant can be of two. We have one which is 0.08205. We use this constant whenever. Now, most of the time we use this constant. There's another constant we can use, but I advise you to use this constant most of the time. And I'll give you when the criteria to use this constant. You just relax and listen very well. Now, moving further, T is temperature, and temperature must be expressed in Kelvin. And I will teach you how to convert temperature from degrees Celsius to Kelvin. And change in N, I will explain. You just relax. So let's solve a practice question based on this relationship. Okay, guys, let's get into this question. It's very simple. So the question says, if the Kc for the reaction below is this. So they've given us the Kc already to be what now? 9.60, 9.6. Now at this temperature, so temperature was given to be 300 degrees Celsius, and I told you convert to Kelvin. How do you convert temperature from degrees Celsius to Kelvin? It is simply Kelvin is equal to degrees Celsius plus 273. So Kelvin will now be equal to, what was the degrees Celsius value? 300 plus 273. So basically 300, all right, plus 273, that's 573 Kelvin. So 573 Kelvin. So this temperature will now be 573 Kelvin. So this is the temperature we're using. You get. All right. What is the Kp? So the question is asking us for Kp. This question is extremely very easy. I've given you the formula you need to know to solve questions under this aspect. And what is the formula? Very simple. It is simply Kp is equal to Kc, open bracket, RT, raised by of change in number of moles of the gases involved. So relax. All right. This change in number of moles, this is how it's calculated. It is simply solved by saying number of moles of product minus number of moles of reactant. This is what I mean. So you look at your reaction and add the moles you are having. So this is my product side. What's the total mole I'm having? I'm having 2 moles minus. Now, if you observe, now this is my reactants, all right? So first of all, add them together. What's the moles we are having here? We're having 4 moles together. 1 plus 3, 4 moles. 4 moles, you understand? So it forms my reactant. Hope you are getting the point. They are all very simple. So it's now be changed the number of moles will now be equal to 2 minus 4. That's minus 2. Hope it's clear. It's very simple. And I told you that Rho is a constant and the constant is 0.08205. And I told you it's best for you to use this constant all the time. And our Kp answer, we are looking for Kp. So if you are using this arrow, our Kp answer will be in atm. Please take note, if you are using arrow to be this, your Kp is pressure. We have various units which can measure pressure, but if you are using this constant, our Kp should be, our Kp must be in atm. This must be noted. All right, let's input everything into our formula. So what becomes Kp? Kp will now be equal to Kc. Kc is 9.6. So here it becomes 9.60, just 9.6. Open bracket means that this is times everything inside the bracket. What's the arrow? 0.08205. So 0.08205 times the temperature 573, all raised to the power of what? Now negative 2, because that was the change in number of moles we had. So you can see how all of these things was tackled, not difficult. Let's impute. All right, all raised to the power of minus 2. What becomes our Kp? Our Kp answer, solve carefully, 0.00, all right, 4343 atm. Because I told you, whenever you are using this arrow to be this, your Kp answer should be in atm. But if you are using the other units, which I will not talk about, because if you know this, you are good to go. So you just relax, they are all very easy. So guys, we've come to the end under this topic, chemical equilibrium. If you find my video lesson helpful, make sure you click on the subscribe button to my channel and also share my lessons with your friends. All right. Thanks for watching.
To have more understanding about chemistry calculations and solving all of these type of questions, I already have them on the chemistry masterpiece, okay, which is calculations and keynotes in chemistry. So if you are preparing to write the JAM exam, this book is very, very important for you. Now, for more information getting the chemistry masterpiece, do well to direct message me via my WhatsApp number. It will be on the screen.